Okay, let me waste my time for my oral English. I want to read this paper. Diffusion models for adversarial purification is published in ICML 2022. The authors are from NVIDIA and Caltech. Links. This slide contains English and Chinese because I don't want to write a English version of a slide. So let me waste but save my time. Okay, the idea is very straightforward and simple. As shown in the title, they use a diffusion model for the pre-processing of images, or they use the diffusion, actual diffusion model to purify the image. So given an image, given an input image X, maybe clean image or adversarial image, we use the diffusion model to add some noise, like the diffusion process, and then denoise the noise from the image to reconstruct the image. So if the input is a clean image, hopefully we can reconstruct the original image. And if the input is adversarial image, ideally we can, after we add the noise, and we can remove the noise with the adversarial perturbation or the adversarial signal together. We remove the signal while it can still keep the label information. So this is a basic idea. And the mechanism behind it maybe just because I think it's just some intuitive, a very intuitive idea. So they have many proofs, very difficult for me. And then they design the adaptive attack because for this method, the regular PGD attack or the auto attack can't apply directly or straightforward directly on this defense method because it have a sequence of steps. So they need to design the corresponding adaptive attack to verify the robustness of their method. Okay. Yeah, let me. So I draw this figure, but I don't think. I think it explains a bit, but maybe it's still useless. Okay, so suppose this is the clean image and the minus is the adversarial image. So if we apply the diffusion process with a certain amount of noise, it can add noise until the Gaussian noise until to the totally noise image. We indicate noise with using the red point. Yeah, you know the drawing. My drawing is very ugly. Okay, so suppose the path. Of course, the path is not. Is very. It has. It's not very. Have some range. So this through the clean image and the adversarial image, they may meet the diffusion path may meet at some certain point, and of course after that they can always use. Then at this point, if they apply the denoising from this image, then it will follow the gradient path. If for okay, they may follow the red path to denoise, and finally go to this yellow yellow star image as the purified image. This one should very close to the clean image and remove the adversarial noise. But if you denoise with a very small perturbation, a very small Gaussian noise, it may. Let me see. If you go denoise from here, maybe it will go back and come here. Then they still contain the. It may still contain the adversarial signal. So the noise they need to choose the lower bound of the noise. And if you add the very strong noise, then suppose they go to this point, and then from here, from this image, the reverse procedure, the denoise procedure will reconstruct to another image, because like a bird, suppose it reconstruct to a bird, then it shows it already removed the label information. So the problem is how to select the best T during in the past. Okay, I think the explanation is redundant. Just waste of time. Okay, let's see the results. We can see their method compared to other purification based methods. Especially this one should be diffusion score model. I think with Langevin dynamics, the performance, the improvement is the dramatically improved performance on different datasets with different attacks. Okay, so it's a very good direction. They use an extra extra diffusion model. The diffusion model can work as a generative model, and here it shows it can also utilize for the adversarial purification. Then you can focus on each model to improve their own main performance, like generative performance or the classification accuracy. Okay, never mind. So yeah, I don't know. I didn't carefully check their proof, but we can see here how to choose the T, how to choose the noise. They have the empirical trade-off experiments.